Restriction mapping is looking at how a piece of DNA is digested or chopped up into smaller fragments by restriction endonucleases. Also, you'll see them called restriction enzymes. In the examples that we're going to be looking at, the DNA happens to be a circular piece of DNA, a plasmid. So it's circular and it's double-stranded. Now, restriction enzymes have got very specific sites at which they can cut at. For example, if I was to take the enzyme KPN1, the restriction enzyme, the only sequence of DNA that it will cut at is when it sees a sequence of DNA like this, and the enzyme will cut between the two Gs. Another enzyme will have a completely different specificity. So for example, BAMH1 will cut at this DNA sequence here, double G, A, T, C, C. And again, it cuts between the two Gs. EcoR1, for example, will cut G, A, T, T, C, and it cuts between the G and the A. Now, I don't know those restriction sites, the sites where the enzymes cut. I don't know those restriction sites off the top of my head, and you wouldn't need to know them either. You look them up in the book. But what you do need to know is that the enzymes will only cut when they come across a sequence of DNA as we see it here. Now, if you can imagine our circular plasmid like this, and our circular plasmid is double-stranded DNA with a whole section, a whole sequence of unknown nucleotides. Now, if our plasmid had sequence A, D, G, C, I'm making it up, and then G, G, T, A, C, C, and carried on A, C, C, T, T around here. If this was to be the sequence of DNA running in our plasmid, and I was to digest this plasmid with KPN1, the enzyme would find the restriction site that it was able to cut at, and it would cut the plasmid at its restriction site there. And if the plasmid was cut once in a position like this, my circular plasmid becomes linearized, and I get a linear piece of DNA. Let's imagine another plasmid down here, again with an unknown sequence of DNA running all the way around the plasmid. And in this example, I've got a BAM site, GGA, TCC, nucleotides running all the way around here. And imagine that there was another BAM site, GGA, TCC here, nucleotides all the way. If I was to digest this plasmid with BAMH1, BAMH1 has got two restriction sites. There are two sites that the enzyme is able to digest this DNA. So BAM is going to cut there, and the BAM enzyme is going to cut there. So my circular piece of DNA has been cut twice, and I have left with two fragments of DNA. I have no way of knowing how many fragments I have produced, or what size, what molecular weight those fragments of DNA have, until I have run them out on an agarose gel. If I was looking at an agarose gel here, and let's imagine we've got molecular weight markers, nice and simple, coming down here. Let's say this is 7 kb, 6, 5, 4, 3 kb. Only when I ran this sample here on an agarose gel, let's say it's a 7 kb plasmid, would I know that by cutting with KPN1, I have achieved a single fragment of DNA at 7 kilobases. My BAMH1 enzyme cut here, and it cut my plasmid into two fragments. Let's say this one was 4 kb, from here to here is 4 kb, and from here to here was 3 kb. And only when I ran this on an agarose gel would I be able to see this, that I have actually got two fragments. One of them was 4 kb and one of them was 3 kb. And we can see that the two fragments here that were cut with BAMH1 add up to give me the 7 kilobase that is the total sum of the plasmid. The complication arises when I do a double digest of that circular plasmid. So we're looking at the same plasmid that we were looking at earlier. It's 7 kb in size. I know that my KPN1 cut in one position and gave me a 7 kilobase fragment. And I know that my BAM-H1 cut in two positions and gave me two bands, one of them 4 kilobases and one of them 3 kilobases. Now, if I do a double digest, in this example, I use the KPN1 and BAM together, a double digest of the plasmid gave me a different pattern of bands. And in this case, I have a band here at 3 kilobases and a band at 1 down here. So the complication is trying to figure out how did I manage to get this banding pattern and where do the restriction sites occur in relation to each other on this plasmid. Now, one of the things that we have to be sure of is that our banding patterns, the bands that we achieve, always will add up to the total sum of the plasmid. In this case, it was 7 kb. KPN1 gave me a band at 7 kb, that's fine. BAM-H1 gave me two bands, 4 kb and 3 kb, so that's fine, that was 7 kb. And when I did a double digest, I've got a band at 3 kb and I've got a band at 1 kb, which only results in a 4 kb plasmid. Now, DNA can't just disappear, so the explanation for the missing amount of DNA, first of all, I need to find out how much DNA is missing. Well, it's 7 kb minus 4, I'm missing 3 kb. And what's happened here is that on the agarose gel, I've actually got two bands at 3 kb, two bands that have migrated to the same position. And on an agarose gel, I have no way of knowing how many bands there are of that size. So in actual fact, I've got two bands of 3 kb and the 1 kb band. And I want to be able to map on to my plasmid where these enzymes are cutting to achieve this banding pattern. So from looking at the agarose gel, we could see that doing a single digest with KPN1 gave us one fragment of DNA at 7 kb. Doing a single digest with the BAM-H1 gave us two fragments at 4 kb and 3 kb. So we could see that the BAM must have two cutting sites. And restriction mapping is trying to map the restriction sites of all these enzymes into relation with each other. There's no hard and fast rules for doing it. The way that I would normally do it is to draw out both of my single digests on these plasmid maps here, and then do a plasmid map of the double digest of the two enzymes together. And generally, I find it easier if I draw on the more complicated enzyme first. So on this plasmid, I want to see where BAM cuts and I want to see where KPN1 cut in relation to each other and how I will generate these bands here. So my BAM is going to cut here and here, and that still gives me a 4 kb band here and my 3 kb band here. Now the bands that I got from my double digest was a 3 kb, a 3 kb and a 1 kb. So how can I imagine where the KPN1 cut to give me these bands? Well, I've already got this 3 kb here, this BAM to BAM was 3 kb, so that's one of these taken care of. And what's left over here was 4 kb, and I need to split my 4 kb into 3 kb and a 1 kb. So I can imagine that my KPN1 cuts here, splitting this 4 into a 1 and a 3. And that's all the bands I saw on the gel resolved. Another way to think of it, and this sometimes helps, is if I was to imagine my plasmids like this. Imagine this is a circular plasmid and it has got two restriction sites here for EcoR1. And here's the same plasmid, and I've shown on this plasmid the restriction sites for another enzyme, XHO1. So this is how the plasmid gets cut with XHO, and this is how the plasmid gets cut with EcoR1. And restriction mapping is when the two enzymes are cutting together on the same plasmid, and I'm trying to find out how these restriction sites relate to each other to generate bands of the size that are represented on the agarose gel. So this is really what we're trying to do. So the bands that occur reflect what we see on the agarose gel.